Hello again, I'm Scott.
I'm Bernie.
And we're here to help you out with Engineers of the Future. So in previous lessons, we talked about building and decorating a bridge. This is that bridge. We talked about testing the bridge. How do we test the bridge?
We break the bridge.
We break the bridge. We need to know how much load it can support. This is the apparatus to test the bridge. We constructed this to create a stable, rigid platform where we can apply load, measure load, and test the bridge to failure. What we have here is a simple adapter to connect to the bridge so that it can slide across and we can connect the crane scale. The crane scale is a unique device that uses a couple of interesting material and physics tricks to actually measure the tension being applied, which relates to the load that's being applied to the scale. This is just another adapter, but here we have a block and tackle. It's all mechanical advantage. It will be multiplied, so we don't have to pull down with 140 or 150 pounds of force. We can pull on that rope with maybe 20 or 30 pounds of force, maybe 40 pounds of force at most. So what you're going to see when we test this is you're going to see the bridge will flex a little bit and it will twist a little bit, and then you will hear some cracking. And when the tension stops rising, we have a hold function on here. When the tension stops rising and starts to fall again, that means that the bridge has failed and we will stop at that point. Now, the way that the bridges will be scored is the amount of load that they support divided by the weight of the bridge.
Weight of the bridge.
So, we already have weighed this bridge, and this bridge weighs, well, it's the lightest thing that we're going to test today. We've also decided that we're going to show you a few analogs of bridges. Because when you go out into the woods or into the desert and you find something, you put a bridge, put a 2x4 across, and everybody scurries across the 2x4. It's an easy bridge. But how strong are they? So we have a 2x4 here. It's going to be much stronger than this bridge is, but it also weighs almost 8 times as much. So the way that you're scored is load divided by weight. So it would still be a fair fight. There are a few other pieces that we have here. We have a simple piece of plywood to act like that simple beam. We have a piece of dimensional lumber, roughly 4/10 of an inch by 2 inches. We have a cobbled together I-beam, which weighs very little. And we have a 1.5 by 1.5 beam that weighs almost a pound. And each of these will be tested after we break our lovely little bridge here. Now, what we also have here for you to see is an example of how an artist who works for Valley Metro might decide to make a bridge a little bit more visually appealing. Just an example. It's just to show you what you might do with some simple paints and colors to make the bridge look less like a chunk of steel. So, as we told you, we've got a couple of analogs. We've got a 1.5 inch by 1.5 inch maple or poplar, maybe it's alder. It's a hardwood alder. Okay, good and strong, obviously good and strong. It's not going to flex at all under my weight. I'm not a lightweight. It weighs
2x2 weighs about 15 ounces and 3/4.
15 3/4 ounces, just about a pound. So from that we've converted that to pounds.
Converted to pounds, 15 3/4 is 0.9844 pounds.
Okay, so that is that analog. This is a cobbled together I-beam. It is quite literally just a couple pieces of scrap wood glued together to form a structural member. And just to give you an example, this weighs
approximately 6 ounces, which is converted to pounds at 0.375 pounds.
This piece of plywood weighs
6 ounces and 5/8 converted to 0.40625 pounds.
Okay, so just as a quick example, they weigh roughly the same. I'm just going to push down on the middle, and you can clearly see the piece of plywood flexing. It's really clear, and I'm not really pushing that hard. Now, if we put this beam there, and we push, is there any flex?
I do not see, Mr. Scott.
I don't feel any flex, and I'm putting 2 to 3 times the force on that. Okay. So the last piece we really have here that's going to be a bridge analog is
Weighing at 6 ounces and 1/4.
6 1/4. So these 3 things all weigh about the same.
And that will
Okay.
be 0.390625 pounds.
Okay, so again, we have a little bit of flex out of this board. Not a lot, but just a hair. It'll certainly support a fair bit of weight. But how much weight will they all support? Then we have the piece of plywood. So this is something that we used 2 years ago almost.
Yeah, about 2 years.
To test that and see how much force we could put on it.
2x4, we are weighing in at about 1 pound, 5 and 7/8 ounces, 15 and 7/8 ounces.
Yeah, almost 2 pounds. Almost 2 pounds. And when we did a brief test again to make sure that it wouldn't break, we got up to 140 pounds and it hadn't started to give yet. So that will be the last thing we test if we choose to test it. So clearly, this guy is the lightest of this bunch. But when we weighed the bridge, what did it weigh?
It weighed about 4 1/8 ounces, which converts to 0.2578 pounds.
So it's just about 60% the weight of this. And it's that big. So that's the beauty of a truss. That you can put a lot more structure together, gain a lot more physics advantage, mechanics advantage, and still weigh less. So this weighs 1.5 times what that weighs, which means it has to support 1.5 times as much weight as that before it'll win. Shall we move on to breaking the bridge?
Let's move on, Mr. Scott.
Okay, so here we are ready to start.
Yep.
Bernie is going to apply tension. We've got everything rigged up. We've got the crane scale set to hold. And down. We're gonna get started. We're up to 40 pounds, 50, 60, 70. Start to see it flexing. Keep going. There we go. And it just, keep going. We're gonna go until we break it. 78, we got to 80 and then it dropped off. Keep pulling. Still not getting any higher. 78.6 is the highest. Keep going. Notice it's folding over, twisting,
Why is the value not changing?
because it's not getting above that.
okay.
So you're applying tension and the bridge is just cracking. So we're done. So this bridge supported 78.6 pounds of tension. And we will take this up like that. Pop that out. Okay. And this is what the bridge looks like after 78.6 pounds. So clearly we expect you guys to do a better job than we did. But where did it break? So did the trusses break? Not really. The trusses are still fairly solid. It's all the ties together that broke, and then it was able to twist over and bend. So if you had more cross bracing and better cross bracing, perhaps it wouldn't have broken. Perhaps if this cross brace had had a piece of popsicle stick underneath to hold it together better. Because it's the ones on the top that seem to break from the twisting first. So now we should test a couple of analogs and see how quickly we can get that done. Okay, so here we have our analog bridge. This is the cobbled together, and it's going to fail very quickly because it twisted. I-beam, we have it up for test. We are ready on hold, and
All right,
we'll
take it
begin.
away.
Bernie, pull away.
We will begin.
£20. Keep going. We're at 26.8 and 28, 30, 31, 32, 30, 47, 84, 95. So,
And our hold value is at 95.0 pounds.
So it should be pretty clear what happened. The glue holding the web of the I-beam to the beam failed. And it clearly pulled the paint right off. Remember, this was cobbled together from a couple pieces of wood. Didn't weigh a whole heck of a lot. Only one piece of wood actually broke. That one, the bottom one. And you can see where it cracked. And it doesn't look like it was it might have been a seam. These are sometimes seamed woods. So it's possible that that was a seam with little tongue and grooves. But 95.0 pounds. This was the simple analog piece of flexible plywood, 1 inch or 1/2 inch by 2 inches. We don't expect this to score anywhere near what either the bridge or the I-beam did. So, you ready, Bernie?
Yes, I am.
Let's go.
All right.
10 pounds, 20 pounds, 30 pounds, 45, 60 pounds, 70 pounds, 78. And now we're ready to go. We have the other bridge analog. This is simply a 1x. It's approximately 3/4 of an inch by 2 inches again. Based on its flexibility, we expect it to support a lot more than the plywood. And because of that, Bernie has another little piece down there to help him get some mechanical advantage, as well as safety glasses. So, are you ready, Bernie?
I'm ready.
Let's go.
All right.
We're at 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, and we're starting to see it flex. Now, part of the issue we're going to have is that this string, this rope, is going to stretch a bit and absorb energy. We're up at 180 pounds.
Oh.
And as you can see, that's pretty amazing given that he's doing it one-handed. 180 pounds. 208.
Man, yeah, it's still going. Man, it's still going.
259 pounds. A pine board, pretty strong. 287 pounds. Sweating over here. Whoa, it just registered 306.
Woo. 306.8, 320.2. 320.2.
Not even a crack.
First crack.
361.6. Wow.
Ready?
Here we go.
Still haven't gotten over that 360.
361.6. We're at 361.6, team. 364.4. Heard a couple cracks.
It ain't giving.
Yeah, it's cracking. That rope's going right through it, but it's yet to break through the middle. It's right about here, about getting through here. Now, mind you, it's a rope though. 396.2. Look at that, everybody. Almost 400 pounds. Round of applause for Mr. Scott Tollefson.
396.
396.2, kids.
Wowza.
Look at that.
Wowza. So we started with the bridge, which only weighs 4 1/8 ounces. We were able to pull 78.6 pounds. And the trusses never failed. It was the connectors. That's a 304-to-1 ratio. The I-beam, which is nothing but pieces right here, right now, completely catastrophically failed, only weighs 6 ounces. It had a 253-to-1 ratio. When we did this broken piece of 1 by something, we pulled that to 396 real pounds and a 1,000-to-1 ratio. The 1/2-inch plywood, so 78 even, but it weighs more than the bridge. 78 divided by 0.40625, 192-to-1. So plywood, very strong, 192-to-1. The I-beam, which was much lighter, was 253-to-1. The bridge, which was lighter yet, was 300-to-1. But one piece of God's good earth pine board, 1,000-to-1, which is why wood is such a good building block. That tells me that we won't even be able to get close to this one. So we know that both the 2x4 and this unit will do better because this is essentially the same as that and it's just twice as thick. It's going to be at least twice as strong, which means we would have to put 600 pounds out. As you've seen, we can break almost anything. We elected to not break the 2 big boards because neither of us really wanted to hurt our hands that badly. 396 pounds for that little board on a point load spanning 20 inches. That explains why houses can be made of wood. So in the past, engineers have done destructive testing like this to determine the actual strength of materials. They still do this kind of thing if you go on to college and take a mechanics course. You will destructively test materials: concrete, small pieces of steel, steel tubes, aluminum tubes, wood, plastics, probably a lot of composite materials. In a simple test like this, it's clear. Mother Nature does a really good job with wood. It's stronger than the plywood. It's stronger than our little I-beam in terms of ratio, 1,000-to-1. But the bridge, a truss that weighed less than 1/4 ounce, that got a 300-to-1 ratio. The I-beam, which was cobbled together out of pieces that we shouldn't have done it with, well, that got a 253-to-1. Plywood, a lot less. So we're looking forward to seeing what you guys can put together for a bridge. We're going to encourage you to do your research and figure out if we did the smartest truss or if there are other ways to do it, better ways. We'd love for you to find a better way and bring it to the table and show us that it's better. Numbers don't lie.
Sure doesn't.
So we look forward to seeing you live on a couple of occasions, and we hope that you enjoy the rest of the videos. And feel free to go through them, do your research, and sort out what kind of bridge you really want to build. Obviously, trusses are very easy to build, very strong. You might find that you can build an I-beam. You might find that you can build a tighter truss that has a much stiffer cross-section and won't twist. Think these things through. We'd love to see what you come up with.
Good luck, everybody.